progress.
So now we want to continue in Lumerical mode to calculate the optical performance of electro absorption modulators. So our I focus on this type of modulator, gas electro absorption modulator. You can find the example of this file from here. So actually we will focus on quantum confined Stark effect that I described in my previous talk. So in the optical performance and optical mode calculation, so let's go to the structure first. So this is our device model, and our device model is a PIN semiconductor. So, and the N type, you can see a gas and superlattice. I will describe how we can create a superlattice, and you can see the different dimension of gas and superlattice, and the quantum well and core and cladding. So let's first discuss about superlattice material. So let's go to the Lumerical mode, and I right click on the mode, and if I select edit object, so in the setup part, I define this variable, start wavelengths, stop wavelengths, number of points. So superlattice material 1 is gallium arsenide, and material 2 is aluminum gallium arsenide. And so how we can define this material? Let's first I defined gas material. So if you come back to this description, you can download the 3.5 semiconductor optical material data tools here. You can download the tools from Ansys website. And if you run the script, you can see this GUI, and you can define your composition of, for instance, aluminum gallium arsenide part, X. And so first I can open the GUI, and you can, this is the script, just this for GUI. It doesn't matter to know about this script, but if I run the simulation, I can select algas adachi, and then I can put the X to 0.3, and I can define the wavelength range. So then I can add the material. So the material is added to the material part. You can find here algas. You can actually define other composition, other parts like different. You can find the different material database here. For instance, in indium, aluminum, gallium arsenide, you can define X and Y, and easily you can add it to the material database of Lumerical tools. So now again, we come back to the edit object and setup. So now I can use the material that we defined. So for the superlattice material one is gallium arsenide, and we define this variable. And if I go to the script, start wavelengths is the start wavelengths of refractive index of data, stop wavelengths of refractive index, and superlattice material one, name of first superlattice material. D1 is the thickness of first material superlattice. And actually we want to generate a refractive index of superlattice. So it's very easy. You can generate a lambda by line space command, and then calculate the F, and then you can calculate the average index of superlattice. It's very easy because we defined our superlattice material 1 and superlattice material 2. So we get the index of these materials, this database to the index 1 and index 2. Then we will calculate the index superlattice just by this formula, index 1, superlattice dimension 1, index 2, superlattice dimension 2. And then we can set the material to our database. So set material, this sample data to the superlattice. So let's click the test. So it works, and apply. So okay, the superlattice is added to our material. You can see here. So I can plot the material. I can go to the material explorer. I need a solver, so let's call an add solver. Just I want to show the superlattice plot, so I can go to the material explorer, and then I can select superlattice, and then plot the superlattice here. You can see that this is the refractive index versus wavelengths of lattice. So now our superlattice is added to the Lumerical mode. So now we want to create this geometry in the Lumerical mode. So let's create these geometries. I defined before. So this is gallium arsenide top. We can go to the gallium arsenide top and edit object, and you can see our material is gallium arsenide. And this is superlattice top. If I go to the superlattice, the material is superlattice that I have added before. Superlattice type 2. This is our multi-quantum layer I will describe. Superlattice bottom 2 and superlattice bottom 1 and gallium arsenide. In terms of dimension, you can see that the dimension of gallium arsenide is 0.3 micrometers, and superlattice bottom 1 is 1.3 micrometer, exactly the same as this structure. So now, regarding to the multi-quantum layer, again, we can create actually group from here, and then if I right click on the edit object, I can define this variable for the multi-quantum well. Actually, I want to create this structure, gallium arsenide, superlattice, gallium arsenide, superlattice, gallium arsenide. So let's, so we have it, so our thickness, our barrier is 20 nanometer, and our well thickness is 9.4 nanometer. So we have 2 quantum well, so you can increase the number of quantum well here. And our well material is gallium arsenide, and barrier material is superlattice. So if I go to the script, you can see that this this loop actually creates the number, our well structure based on number of well, and our well material is our actually barrier material is barrier material, that is, so barrier material is superlattice, and our well material is well material, which is gas. And that's it. So it's our quantum well structure. We can create a multi-quantum well layer here. We can also zoom the quantum well part, and you can see the, for instance, this is the barrier. If I go to the material, this is superlattice, and the geometry is 20 nanometers height. So our well is gallium arsenide, barrier 2, well 2, and barrier 3. So now we create our structure according to this geometry. So next step, in next, actually, we need a solver, so we can add FD solver here. So this is our FD solver, you can see, and our FD solver is 2D normal, and boundary condition is metal. And but another thing that we have added another mesh, mesh overlap here to increase the accuracy of our calculation. The DZ in this mesh override is 1 nanometers. So now always now we can see the results. So if I run the simulation, go to the model analysis and do the simulation for this wavelength 0.85, and I want to find the mode. So calculate the mode. So I'm waiting to see how many mode I can see in this structure. So in the mode calculation, all of the mode appears in this part: mode, effective index, wavelength, loss, and other parameters. So for instance, this is our first mode. So the effective index is 3.5, wavelength, loss, T, polarization, TN, and different modes. So we want to see a different mode here. So we want to focus on this mode. So in this mode, we want to actually calculate the confinement factor here. If you see in my slide, confinement factor is the power fraction overlap of optical mode with active layer. So just we can go to the select the power and dense integration, and then we can just focus on our active region, which X, Y, and X2 minus 25 and 25, and our Z start because our quantum will start 1.83 to 1.9088, and this is our fraction, confinement factor fraction. So you can also see here, you can see the 1.83. We select the 1.83 of this part. So next, we can go to the frequency analysis and do the frequency analysis from wavelengths of 0.85 to this wavelengths to calculate the group index and refractive index. So let's do the frequency sweep. So we can ignore this error, this warning actually. So now we are waiting to extract the group index versus wavelength, the group delay, and other parameters that is related to the mode. Just we want to sweep this mode that we have selected, and you can see in this screen. So the progress is 95%, and now the simulation is almost, I think, is finishing, and yes. So this is the effective index versus wavelengths, and so regarding to the extract the parameter, if we calculate the mode, if we right click on the model and if we select edit object, if we go to the analysis, in analysis we define this variable output file name and confined Stark effect, electro absorption modulation of optimization of output, and we are interested to calculate the effective index, group index, and confinement factor. And this is a script, and results, we get the results from FTE data, model 1 and ineffective, and we will put it in the ineffective variable, and group velocity extracted to VG, and NG is calculated with this formula, and then confinement factor from power integration that I showed you before is saved in confinement factor variable, and then we saved these parameters to the output file name. So now I can run the simulation, run the analysis. So our analysis, now we can see the results. So visualize confinement factor. Our confinement factor is 0.06, and effective index is 3.5. So we can see the imaginary part also, it's 0.018, and you can see the group index is around 4.2, And we can go to the actually simulation part and see the file, JSON file, and see our coefficient factor. It's 0.06 and real part and an imaginary part of it, an effective, and this is a group index. So now we want to use this variable and parameters in lumerical multi-physics.